Okay, line integrals along curves in R2 or R3 may also have integrands that involve vector fields. Such line integrals are different from the scalar line integrals in two ways. One, vector line integrals must be evaluated on oriented curves, and the value of the line integral will depend on the orientation. Now remember, when you have a parameterization and the t values are moving from 0 to 10, the starting point would be when t is equal to 0. So it's the point on the curve when t is equal to 0. And as you let t increase, you would be moving along the curve in the positive direction. Okay, so vector line integrals must be evaluated on oriented curves. Okay, 2, the line integral along the oriented curve has to involve a specific component of the vector field. So we're going to look at two different components. One will be the component of the vector field in the tangent direction, and the other one that we'll look at later is the component of the line integral for the vector field in the normal direction. Okay, so now let's say that we have a smooth oriented curve given by r of t equal to x of s, y of s, and z of s. Okay, and we're going to let f be a vector field. Okay, if theta is the angle between f and t, t is the tangent vector at a given point on the curve. Then recall that cosine of theta is equal to the dot product of f and t over the magnitude of f times the magnitude of t. Well, that means then that f dot t is equal to the magnitude of f times the magnitude of t times cosine of theta. But remember that the unit tangent vector t means that it has magnitude 1, so this is equivalent to the magnitude of f times cosine of theta. Now this is the value of the projection of f onto t. It's called the scalar of f onto t. So what it's finding is it's finding the, like if I took this vector f and now project it onto the vector t, I would drop a perpendicular straight down to t, pretend that's a right angle, and the length of this curve, of this vector, that's the length of the projection of f onto t, has magnitude, the magnitude of f times cosine of theta. So that is f dot t. So if we're going to do a line integral of f dot t over the curve C, what we're doing is we're accumulating all the components of f in the direction of t at every point on the curve. So this would be equivalent to the integral of magnitude of f times cosine of theta. Okay, so what we're trying to find is we're trying to find the line integral of the vector field f in the tangential direction. And it's denoted by the integral of f dot t ds over the curve C. Okay, so what we need to do is have a method for evaluating line integrals where the parameter does not have to be the arc length. Now to do that, we're going to take this line integral, which is measuring the components in the tangent direction of the vector field, and we want to rewrite it. Now recall that the tangent vector t is equal to r prime of t over its magnitude. It's that tangent unit vector. And so if we start with our curve r of t, we can get r prime of t by taking the derivative, and then the tangent vector is just the r prime of t vector divided by its magnitude. So I'm going to replace the t with r prime of t over its magnitude. Now recall also in the previous section that we found another way to represent ds so that we didn't have to have the arc length for the parameter s. Okay, and ds was equal to the magnitude of r prime of t dt. So now, simplifying this integral, we could write it as f dot r prime of t dt. Okay, so that's one form. And the nice thing about that form is that we now have the integral as an ordinary integral where t is the parameter, and the limits of integration then would be the values of the parameter t. So from a to b. But r prime, we could write r prime as the vector x prime, y prime, z prime. So this integral could be written as f dot this vector x prime, y prime, z prime. Or we could go ahead and write f as the vector fgh, where the components, each of the components is little f, little g, and little h. There's a lot of different representations for this same exact vector integral. Okay, so then if we go ahead and perform the dot product, we get f dot x prime of t plus g dot y prime of t plus h dot z prime of t, or not dot times, this will be multiplication. Now you can also, if you recall that x prime of t is just dx dt, so we could write dx as x prime of t dt. And so if you took this x prime of t dt and replaced it with dx, that would be another representation. Likewise, the y prime of t dt would be the dy, and the z prime of t dt would be the dz. Or we could even let there be a vector dr represented as dx, dy, dz. And we could view this representation as just the vector field f dotted with that dr. So there's lots of different forms that this tangential form of the line integral can take. So if you see something that looks like any of these, it's the same thing as this integral of f dot t. So now, how we're going to evaluate it, the easiest way to evaluate it is to take this form right here. You have your r, which is your parameterization, find the r prime, take the vector field. You're going to have to represent the vector field in terms of the x and the y and the z, or in terms of t's, functions of t, using your parameterization, and then do the dot product and evaluate. Now, that was the problem if you were dealing with a line integral in R3. So if your curve was in R2, then this bottom one would be your integral. So it's the same form. It's still f dot t over the line integral c, so you don't, over the curve c, so you still don't see any difference there until you start looking at how many components the f and the r each have. Okay, so let's evaluate the line integral where the vector field is y minus x comma x on each of these paths. Okay, so the first thing we need to do, write down what we're looking for. So in part A, we want the line integral. Okay, so we're going to find the integral of f dot t ds, that's just the notation for it. And now that's the same thing as the integral of f dot r prime of t dt. And then we need to know what our parameters are going to be. So first let's get our parameterization. We're talking about the quarter circle C1 starting at 0, 1 and ending over here at 1, 0. So here's the curve C1. Okay, we want a fourth of a circle, but we want it to go in the clockwise direction, not the counterclockwise. If you let x equal to cosine of t and y equals sine of t, you're going to be going counterclockwise. Just look at what the value would be when t was equal to 0. That tells you your starting point. So if I want to go clockwise, I'm going to reverse them. I'm going to put sine of t first and cosine of t second. And now the t value is going to go from 0 to pi over 2. Now let's try it. Put t equal to 0 in. Sine of 0 is 0 and cosine of 0 is 1. So this would be starting at the point 0, 1. And now let's look at pi over 2. Sine of pi over 2 is 1 and cosine of pi over 2 is 0. So we're ending at 1, 0. So just reverse the two components if you want it to change directions. So this is oriented going in the clockwise direction. So now look at our vector field, F, and rewrite it in terms of t using the parameterization you just found. Cosine of t is our y, and sine of t is our x. And then the x, again, is sine of t. So this is the vector field in terms of t. Now, the integral will be the f dot r prime. Well, we need to find r prime. R prime of t will be equal to cosine of t negative sine of t. Okay, so now evaluating the integral, we have f dot r prime of t. Now notice it's not the magnitude of r prime. When you're dealing with the vector fields, you're using the vector r prime and doing a dot product. So you're not putting the magnitude except in the scalar valued line integrals. So this integral becomes the f, which is cosine of t minus sine of t, comma, sine of t, dotted with r prime. And now t, the parameterization that we had, has t going from 0 to pi over 2. Okay, do the dot product. We'll have cosine of t here times this whole difference. So we'll have cosine squared of t minus sine t cosine t plus negative sine of t times sine of t. Okay, so now let's evaluate this. First thing that comes to my mind is I've got a cosine squared minus a sine squared, and I remember a trig identity that cosine squared minus sine squared is actually cosine of twice the angle. So if I can switch this over to just cosine of 2t, that makes it much easier to integrate. So cosine squared t, it's just a trig identity, it's double angle formula for cosine, minus sine squared t is cosine of 2t. Okay, so now continuing, another trig identity that comes to mind is the double angle identity for sine, which is sine of 2t is equal to 2 times sine of t cosine t. Well, I've got sine t cosine t here. When I have that product, it makes me think of this identity, and sine t cosine t then could be written as 1/2 sine of 2t by taking the 1/2 of both sides. So I'm going to change this part to just 1/2 sine of 2t. Now both of them are just single powers of the trig function sine and cosine, and I can easily integrate. So this will be the integral of cosine 2t is 1/2 sine of 2t. And then the integral of 1/2 sine of 2t will be 1/4. Now it's going to have to be the opposite sign. So plus 1/4 cosine of 2t, since the derivative of cosine is negative sine. Evaluate from 0 to pi over 2. So I have 1/2 sine of pi plus 1/4 cosine of pi minus 1/2 sine of 0 plus 1/4 cosine of 0. So now we have sine of pi is 0, sine of 0 is 0, cosine of pi is -1. So this will be -1/4, and then cosine of 0 is 1. So it'll be -1/4, gives me a -1/2. Okay, so that's the vector field line integral from P to Q. Okay, now let's look at the quarter circle going, it's the one defined as -C1. So it starts here at Q and it's going to end at P. So now we're going in this opposite direction. So the orientation is counterclockwise now. So now we know how to define a counterclockwise orientation easily. That parameterization will just be the cosine t sine t. And the t again goes from 0 to pi over 2. So let's go ahead and find our r prime since we're doing this now. And that'll be minus sine t cosine t. We've already rewritten, let's see, we have to rewrite the vector field though for this new parameterization. So even though you did it over here, you've got to, in the first part, you've got to redo it for each parameterization because your x's and y's already have changed. So this is y minus x comma x, which will now be sine sine t minus cosine t, comma, cosine t. Okay, so now the line integral. F dot r prime will be sine t minus cosine t, comma, cosine t, dotted with the vector minus sine t, cosine t. And our parameter goes from 0 to pi over 2 again. Okay, so this equals to negative sine squared. It's the integral of negative sine squared t plus sine t cosine t plus cosine squared t. And then dt. Now again, we've got this trig identity. We've got cosine squared is positive minus sine squared. So those together make cosine of the double angle. And again, I have the sine of t cosine t, which is 1/2 sine of 2t. Okay, cosine 2t will have integral of 1/2 sine 2t. And then plus 1/4 negative 1/4 cosine 2t. Okay, evaluating. We have 1/2 sine of 0, of sine of pi, which is 0, minus 1/4 cosine of pi, which is -1, minus 1/2 sine of 0, which is 0, minus 1/4 cosine of 0, which is 1. So we get 1/4 plus a 1/4 gives you a 1/2. Now notice here that the curve, it is the same curve, but now the orientation is different. And notice that the values of these came out to be the same absolute value, but they had opposite signs. So when you change directions, it does make it the negative of the other, of what the other direction's line integral would be. Okay, so now let's look at our third path, which will be C2. C2 will go from P to Q, but it's going to go through 2 line segments through the origin. So the first part will be here, and then the second part will be here. So we're going to need 2 different parameterizations to define those 2 different line segments. Okay, so our curve, okay, I'm going to call R1 the part going from 0, 1, 2, 0, 0. So R1 will define that segment, and then we'll let R2 describe the second part of R2 of C2. So R1 of T, our starting point 0, 1. Use that for my x naught, y naught. And my direction vector, if I just take the change in the x's and the change in the y's going from P to 0, my vector v that's parallel would be 0 minus 0 is 0, and 0 minus 1 is negative 1. So that's the vector parallel to the vector passing through those 2 points. So we'll have plus 0t and then minus 1t. So the parameterization is actually just 0, 1 minus t. And now again, the t values will go from 0 to 1. So let's test it. Put t equal to 0 in, we're at the point 0, 1, right here. Put 1 in for the t, we're then at the point 0, 0. And notice here that the x stays 0 the whole time you're on this line segment. Okay, so now let's look at R2. This one starts at 0, 0 and goes to 1, 0. So that parameterization, I'm starting at the point 0, 0 for both components. My change, the change in the x, 1 minus 0 would be 1, so plus 1t. And then the change in the y's is 0, so plus 0t. So that parameterization will actually be just t comma 0. So t goes from 0 to 1. That means when t is 0, we're at 0, 0. When t is 1, we're at 1, 0. And we've just described that curve. Okay, so now let's go ahead and find the derivative of each one. So we're going to have the derivative of 0, 1 minus t will be 0, negative 1, and R2 prime will be 1 comma 0. Okay, so now for each parameterization, I need to write the vector field. The f, which was y minus x comma x, can be written as, now come back up here to your x and your y. The y is 1 minus t. The x is 0, minus 0, comma x. So that will be 1 minus t comma 0. And the second part over here, the vector field, y minus x comma x, y minus x will be 0 minus t comma x, which is t. Okay. Okay, so now let's find the vector, the line integral. F dot r prime of t. Now this is for the first portion. So for the whole thing, f dot r prime over the curve C will be, it's actually C2 is the name of the curve. We're going to do the part from 0, 1 to 0, 0 first. So let's go ahead and just write the vector field here would be 1 minus t comma 0 dotted with the r prime for this particular path. Okay. And that was t going from 0 to 1. So I'm just using this vector field and this tangent vector. And then we need to add the other one. So the f over here would be negative t comma t, and the r prime would be 1 comma 0. And again, we're using the parameters values for our limits of integration. Okay, just do the dot product. This will be 0 plus 0. Well, that one's not going to have much of a value. And we come up with a negative 1/2. Now notice that this value is the same as what we got in our first integral. We got minus 1/2. We were going from P to Q in both cases. So here we were from P to Q, and from this one we were from P to Q. And notice they were the same value. That's not true for every vector field, but certain types of vector fields, which we'll look at in a couple sections, will have that property where it doesn't matter what path you go on. All it matters is the starting and ending points of that vector field. So that's just special cases of the vector field. But in this case, this is that type of vector field, and we do have the same value for the line integral of any path starting at P and ending at Q.